I'm gonna refresh it. Yeah. But so we got some other things, really important things to do here. Okay, so everybody, welcome back to Utah Zig. We're happy to have you with us. Before we're already kind of late, so we'll just go ahead and get started. But real quick, I'm AJ. This is Ryan. This is Robert. This is JoJo. Matt, and Niles. Niles is presenting today on hyper-optimizing the Zig parser.
Yep.
So strap in your assembly seats.
Yeah, there's going to be a lot of that.
Buckle up your SIMD. Let's do this.
Yeah.
Niles, take it away.
All right, let's go to the first slide. But thank you to AJ for organizing this, and to Vivint. I made a cool little animation for you guys because you waited so patiently.
You made this while we were waiting?
Yeah. Accelerating the Zig parser.
Is there sound effects? It feels like there should be sound effects.
You have to provide your own. It's kind of a budget ordeal.
Oh well.
Yeah.
You didn't want to just rip off Stranger Things or something?
Maybe for the next one I will.
Yeah.
But yeah, my name is Niles Salter, and my talk is on the Zig parser. And let's go to the first slide.
Oh, whoops! Hold on. I noticed just something's wrong on the screen here. It's got the wrong name, and that's just because it didn't refresh. Nope. I'm very confused. Give me 1 second here.
I hope the audience saw that animation.
Yeah.
Yeah, it's cool.
I hope so. It was the whole reason I came.
Yeah. Wait, we might have to replay it for Jeff.
We might have to replay it.
Yeah.
Yeah. Technical difficulties one more time.
I love technical difficulties.
All right, we're not really going to take
I
the whole 10
live
minutes.
for technical difficulties.
But
That's why you like me?
okay.
I like Zig because it's simple, and I don't have to deal with, module resolution and get submodules. I don't know.
Okay. There we go. We got the some streams got crossed and the wrong date and presenter and all the things is showing up, but it'll be solved momentarily.
Okay.
If I can just get the file digged. All right. 5, 4, 3, 2, 1, reboot! Okay, so we're going to take it from the top.
Okay.
We're going to take it from the top for everybody's enjoyment.
Okay.
I'll do the little refresh, and we'll wait the 30 seconds for the animation. Okay, welcome everybody to Utah Zig. And Niles is presenting today on hyper-optimizing the Zig parser. Buckle in your SIMD seatbelts and put on your ASM hat because here we go.
All right. Thank you.
And then if I can get it. All right.
All right. You want to full screen it maybe, or?
I did full screen it.
I see
No,
stuff
like
at the top.
F11, dude.
Yeah, but that's just how browsers work these days. We've forgotten how to do full screen in browsers. I'm not kidding you. We can talk about that later, but
Wait,
Jonathan Blow.
You can't do FN F11?
It doesn't work.
Doesn't work.
Prove it.
Okay. It is full screened.
Really?
Yes, it is full screen. This is in full screen.
Mac full screen.
I can
Browser full screen.
I can explain it later, kind of, sort of. It is, but it is full screened. I apologize. That is what you get for a full screen these days.
Really?
Let's just scrap the whole
Let's just rewrite everything.
all of Mac, scrap it.
All right. Well, my name is Niles Salter, and my talk is on hyper-optimizing the Zig parser. I've been approaching the front end of the Zig compiler as an optimization project and trying to rethink innovative ways that we can get more performance out of these things. Can we go to the next slide, maybe?
Yeah.
All right. So I did give a talk in January on a similar topic, but it didn't land that well. So I'm going to cover some of the same things. And I'm just going to do a brief recap of kind of the motivation, if we could go one forward. Okay, so we discussed last time how computers can go faster. That would be that computers face, in a physical universe, computers are bounded by physical constraints. I talked about how computers can get faster in the future, either through the materials or through instruction set architectures getting better. But in general, we have fundamental problems with the universe. So if the reason why thinking about memory and caches is relevant today and will be relevant in the future is because if you have a cache that's a given size and you want information to travel to a particular point in space, if you want to increase the size of that cache, then you will be increasing the distance between the point where you want it to go and where it comes from. And so fundamentally, the trade-off that we have right now for caches is something that we have had for a while and we are going to be stuck with. And yeah, if we can keep going. We want to reduce cache misses. That means that if you do a big O time complexity analysis, sometimes an n log n algorithm is going to scale better than an n algorithm. I referenced a paper that was a performance case study on heaps, and it was actually from the year 2000, interestingly enough, kind of older than you might expect. But they found that once you go outside the size of your cache, it might have been their L2 or their L3, they found that the quote-unquote linear rhythmic time algorithm scaled better than the linear time algorithm for heap construction. So if you guys know about heap construction, it was J.W.J. Williams' incremental heap construction versus Floyd's linear time heap construction. And the problem with the big O analysis is that you were really only considering, you're saying that the function that relates the input size, assuming the input is randomly distributed or not known to have a pattern, you have a function that relates the input to the number of comparisons and the number of swaps, when in reality we can do an extraordinary amount of comparisons and swaps, even within a single cycle. What we cannot do an extraordinary amount of is cache miss. And so the incremental heap construction algorithm is... What's up?
Can you zoom the text?
I cannot.
You cannot?
It is the size that he put it at. I mean, I guess I can do this.
Oh,
Okay.
that's the thing. Can we zoom out a little bit?
You're asking an awful lot. We've got the
All right.
latency of the display. We've got the issues with the full screen.
All right. Well,
I'm recording
yeah.
on this computer.
Point of the story is cache matters. All right, let's go to the next one.
I don't know. Cache matters.
Cache matters. Think about your data. Yeah, that's the study. You can go read it if you read studies, but you probably don't. Reduce branch miss prediction. So we talked about branch misses. Basically, there's a fundamental problem. When you have a multi-stage CPU, there's a pipeline, and it starts out with the instruction fetcher, which is going to feed things into the decoder, which is going to feed things into a very large scheduling apparatus, which eventually is going to go into some executor stage of the pipeline. And obviously, things have to make it through the pipeline in order to get executed. But anytime you see a conditional jump instruction in the instruction fetcher no longer knows where to go. Because if it says, if it's true, go over here. If it's false, go over there. The instruction fetcher doesn't have the information from the executor. It hasn't been computed yet. And so there's a two-way dependency across a pipeline that is not instantaneous to traverse. And in fact, more complicated computers, you can go read about manufacturers who brag about their pipeline length. They have it worse. So as much as we can, reducing branches is a good idea. Eliminating unnecessary instructions, fewer is typically better. Some people like to point out that instructions can have different latencies and throughputs, but when you're working with a compiler, a lot of times fewer instructions is going to be better. Also, as the number of transistors on chips have increased, a lot of instructions have gone towards the 1, 2, and 3 cycle range. And so just looking at the sheer number is actually a pretty decent metric nowadays, just like it was a very long time ago. Improved data level parallelism is another thing we can do. So this would be SIMD and SWAR, which I'll be talking about at length. Let's continue. Oh yeah, and we can move work according to what pass it's cheapest to do it in. So if we have multiple passes within a system, it might be advantageous to do it in a different one. Okay, Zig compiler basics. We convert code and text files into executable binaries. This is a picture of the Zig compiler's internals. It comes from Andrew Kelly's talk on practical VOD. And on the upper layer, you can see the code passes. You have a tokenizer, parser, abstract syntax tree generator, or maybe that doesn't stand for generator because it's consuming an AST. But on the bottom level, you have the data. So you can see how our data is being transformed, and at the end of the day, you want to actually have an executable that you can run. Let's go to the next slide. Okay, so intro to tokenization. Unfortunately, the tokenizer that shows you the pretty colors in my source code, we could not get working.
This is beautiful.
A little bit ironic, but I made this really fun column counts function. It's completely unrelated, but if you go to the next slide, just one. Look at that. We got highlights on those for some reason. All right, well, the point is we want to chunk up the file. That's the point. So if you can click through the next couple slides, you can see we want to get out a kind, which is some enum, which is going to tell us what is in it. And we also have a start and an end. That could be an index, or we might also have a length. And that is basically what we want to do with tokenization.
Okay, so let's slow this down for a second.
Yeah.
Kind is...
Yeah, so kind is going to be an enum, which describes what it is. So if it's a keyword, it's actually going to tell you which keyword it is. If it's a symbol, an operator, it's going to say, okay, this is a plus equals, this is a times percentage. Or maybe it'll just say built in for the at vector. But when it comes to chunk, we're just going to have an identifier.
Okay, so parser goes over determining the type of each token being the whole token until the next token. Okay.
All right, so here's a basic tokenizer. If we could just keep hitting that right arrow, you could see we go character by character, and it's supposed to have a cursor in there. Keep pressing it, see if it appears. Oh my gosh. It's not there.
That's okay.
I think we're missing a file. Okay, well, it's supposed to show you, we're going character by character. You can at least see that as we step through it. I had a little pointer, and yeah, if you can just keep spamming that. The point is, it's going to take a long time because we're going one character at a time.
Oh, okay, cool.
And
So
we
this
don't
is-
want to do that.
So this is showing...
This is like the typical bare bones first like person handwritten.
Yeah.
tokenizer kind of thing.
Yep, so this is a tokenizer that I wrote in like a minute. And it's like the basic way that you would think to do it. You go one at a time. Oh, there you go. Go back, go back, go back.
Go back.
Yeah. So this is a better tokenizer. You see the number at the top that says 16?
I do not.
In the URL.
Oh, I don't have the URL on the screen.
Okay.
Because I
Yeah.
wanted to make it full screen.
Okay, so the point here is we can do the same exact work, but with some SIMD involved. So if you would go to the identifier bit string,
Whoop.
step through it a little more slowly. Okay.
Yours is so optimized, it just goes much faster than
All
the other
right,
one.
so the idea is we can produce a bit string which tells us where the alphanumeric underscore characters are in this case, because we see an alphabetic character, and we want to match however many alphanumeric and underscore characters we see after that. So we produce some bit string, and we're actually producing a bit string that is the size of usize, which is the word on your machine. It's the size of a pointer. And And so you can see we have 1, 1 corresponding to the F and N character at the beginning, then we have a 0 corresponding to a space, and then we have a bunch of 1s corresponding to the characters of column counts. And so everywhere there's a 1, it's an alphanumeric or underscore. Everywhere there's a 0, it is not. And so if you go forward 1, we can feed that into a not and then a count trailing 0. So that will allow us to count the trailing 1s. Which in this depiction is going to be on the left-hand side because this is assuming little endian. And little endian, so if people don't know what that means, little endian refers to the byte order. So if I load out 64 bytes, the least significant, the first byte that's at that pointer is going to go into the least significant position of my 8 bytes that I loaded or 64 bytes for some large vector. And it determines bit order when we're talking about move masks in the context of SIMD, because what we're doing is we're producing a bit string that corresponds to the bytes. And so the bit order corresponds to the byte order. And so in this case, little endian refers to a bit order when we are talking about a bit string that represents byte order. Hopefully that makes sense.
So, sorry, you're doing count trailing 0, so you're trying to just use this to really quickly read how big the current identifier is and then just skip it all at once.
Exactly.
Rather than doing cycles for every character.
Exactly.
But you're not reusing the bit string for the next identifier? Because I see lots of identifiers in the, was 128 bits of...
This one is 64,
64 bits?
assuming a 64-bit machine. The reason for that is because our count trailing 0 can efficiently operate on 64 bits. And you are correct. So that's the next thing that's coming up. But yeah, this is the basic idea. If we could go forward couple until we see the column counts one. Yeah, keep going. So yeah, then we see a space. We're going to come around, we're going to see a space, and then we're going to go back up, and we're going to see it again, produce another bit string, and now we can jump over column counts. Okay. So,
did I do it right?
yep.
Okay.
So like you said, that is not that efficient because it's not completely free to produce those bit strings. It actually is going to take us some time, and so it makes a lot of sense to reuse those bit strings. So if we could go forward.
Are compilers capable of doing this kind of optimization, or does this just never happen?
That's exactly what I'm about to talk about. So here is the bit string generation emit. For some reason, it keeps hiding the code. If you could hit edit on Compiler Explorer, I really don't know what to say about that. And yeah, if you could split screen it at the top left, grab one of those and split screen it. Grab one of the editors down.
Oh.
Yeah.
Grab little tabs.
The little tabs, yeah.
Okay.
If you could split screen it. Okay, yeah, so you can see the code. This is what we're doing. We're just looking at the alphanumeric or underscore, and then this is what it gives you.
Actually, let me do it this way because I can't see that very well.
Okay.
Actually, no matter which way we do it, I can't see it very well. That's
Okay.
All right.
So this way, I'm looking at it.
So is this what we're looking
Yeah,
at?
this isn't that bad. If we could go to Zenver 3 as well, just so you can see what the compiler will do when you switch the target. If you just change that 4 to a 3.
I am looking for
Right in the middle of the screen.
in the middle of the screen. Okay.
CPU right here.
Yeah, so on Zenver 3, you can see it's going to compile differently. The reason for that is we don't have 64-byte vectors. So we can emulate it with two 32-byte vectors, and we're going to need to double up on the instructions of the ands and stuff.
Is Zen an Intel thing?
That's
Or-
AMD. AMD's Zen architecture.
Okay, this is the AMD 64-bit.
Yep.
Okay.
And then yeah, they have a move mask instruction on this machine. It's, if you scroll down a little bit, yeah, right here, VP MOV MSKB. So what that will do is it will take 32 bytes, it will take the uppermost bit of each byte and extract that into, you see that EAX or ECX register, that's going to be a 32-bit register, and then you can see that shift left by 32. So we're shifting one of them left by 32 and we're ORing them together to produce 64 bits of information. If you want, you can check how it compiles on like ARM, for example. So if you change that x86 64 to be AArch 64, yeah, AArch 64, and then you change the CPU target to be, I like to do Apple latest, just for fun. I like the, it's going to be an underscore.
Oh.
Yeah. Zig is actually consistent with the underscores, unlike LVM.
My only weakness.
So, yeah.
These are Zig command. Okay.
Yeah.
All right.
Okay, so if you scroll down, yeah, you can see we have two LDPs at the top. We load in 2 vectors with each LDP. So we're loading in 4 vectors total. We have 16-byte vectors on ARM, and there is kind of a lot of emulation code going on there. And I'm actually going to show how we can make that better in the way that the compiler currently will not. I will say this on in defense of the ARM architecture is actually one thing they do is they actually can get a lot of the same performance that you would see on like the 64-byte vector supported by a Zen 4 or x86 64 version 4. They actually can get at a lot of the same performance by simply exploiting instruction level parallelism a lot more. And so they can run 4 compare equal on 16 bytes apiece in one cycle, which would be the same as on the x86 side having a 64-byte vector and doing that. And so definitely there are trade-offs involved here. And yeah, I want to show one more. If you could do RISC v64.
Is that's the target?
Yeah, that's the Arch. And you can keep Linux, but
RISC v64
dash Linux, and then yeah, I have the sci5 underscore U74.
I probably spelled that wrong.
It's SI.
Without a C,
SI5.
and then VE right there.
Oh, okay.
There you go. Okay, so this is completely unvectorized code. If you actually scroll down, you will see 1,100 instructions.
Holy shiznit.
And this is because this machine does not have vectors at all. But there's something called SWAR, and we actually could be exploiting data level parallelism even on this machine. So that'll be next. We could X out of this. It will be on the next slide if we want to see it.
Okay. I'm going to try to clean that up a little bit and still won't go to full screen.
If you double click the top bar, what will that do?
I'll try it. No.
Nothing.
No, it's
Yes.
this isn't my primary browser and weird stuff.
All right, let's go to the next slide. Okay, so this is the loop emit. I just wanted to show this real quick. If we could just edit on Compile Explorer again. Yeah, if you could do the split screen thing. I just wanted to show the basic code. So before I was just showing you what the comparisons look like. This is in a loop. And I even inverted the instructions so that we avoid the not, because that was breaking LVM until like last week. I actually got someone to fix that.
Oh, that's cool. There we go. Okay.
But yeah, so you can see this is what the loop looks like. It's very tight. So yeah.
And sorry, what was this? This was?
This is just a basic tokenization loop
Something is
emit.
last slide, but just tell me.
Yep. It's just with more context so you can see. So when it's in a loop, you can see that the VP broadcasts are moved up out of the loop. So you're not running those every single iteration. And so you can kind of see what it's going to look like in context, and you're also going to realize that there's going to be some overhead associated with starting a loop for the first time. If you have to load up a bunch of vectors, maybe it makes sense to, I don't know, do multiple 64-bit chunks at once.
So this is the compiler doing common sub-expression elimination, if I'm not mistaken.
With what? Oh, you're just talking about extracting it out of the loop?
Right?
Oh, yeah.
So it's moving the common sub-expressions out of the, or the, what is it called? The constant expressions out of the loop? I can't remember what it's called.
Okay. I guess you could think of it like that. I mean, it's just, yeah. Yeah, let's move on. Yeah, you have to click off of it. Okay, so yeah, this is some SWAR emulation.
What is SWAR?
SWAR stands for SIMD within a register. So this is a way that you can actually emulate this on a machine that does not have explicit vector instructions. If you have 8-byte registers, you can load in 8 bytes at once. So if you could click through a couple here. With V, it'll start an animation. So you can see, whoa, don't skip over these, because it will go through it way too quickly. If you scroll up, go back 2.
This one? Oh,
Okay, yeah, and just do one at a time.
All right. So,
Yeah. Okay, so the first step, we're going to mask all the bits except the highest one. If we go to the next one, I put a dot there to show that it's no longer a bit of information. Then we can XOR with all underscores, or it could be anything. And the idea is that we're going to get all zeros if there was an underscore in a particular place, and we're going to get non-zeros if there was anything else. Because anything XORed with itself is going to be 0. Okay. We can do similar tricks for figuring out a range. So instead of just adding that mask to extract the bit into the uppermost position, which is, the mask is all ones except for the uppermost bit. So that propagates any information to the uppermost bit of each byte. And then with the final few lines here, I'll show how we can extract that out. So go slow here. So we can multiply by a bit string where every 7th bit is set. And what that will do, there are 8 bits set, so we're going to have 8 copies being added together. Each one will be shifted by a different amount of 7. And you can see in the uppermost byte that we can actually concentrate all of those disparate bits into the highest byte. And then we would shift it by 56 to get it in the lowest bit position. And then, and yeah, the code itself, it will actually loop around 8 times. I'm not showing that here. But yeah, the point is we actually can do this. And actually people are working on getting this built into LLVM so that in the future you would not need someone to manually write it out. But,
well, hold on a second. So I lost a little bit of the context here of what we're trying to do. So mask for alphanumeric and underscore better SWAR.
Yeah, the better just means I'm building on the previous slide. This is slideware, I apologize. Okay, but yeah, the point is we're trying to tell where the alphanumeric or underscore characters are. Okay, and what we can do is we can load in 8 bytes at once, corresponding to 8 bits of information that can be produced. And this multiplication here shows how if we can get those bits of information into the most significant bit of each byte, we can move all of those bits with a single multiplication into the uppermost byte. And then from there, it's just a matter of doing this 8 times, combining 8 such bytes to get us up to 64 bits, which we can also efficiently emulate a count trailing 0 over 64 bytes on a machine that efficiently supports 64-bit operations.
So what you're saying is that you can take 64 bytes of information about the character, knowing what type of character it is, and you can compress that down into 64 bits of information. So you are able to do this operation in addition to the other things that you're already taking advantage of. You're now making it yet 8 times faster, again, improved on your previous optimization. Is that?
So what you said up until the end is basically correct. What we're doing basically, we're emulating SIMD, okay? We don't have 32-byte vectors on certain machines.
Oh, okay. All right, got it.
And so what we're trying to do is we're trying to build up that same information. Now, we are still getting speed benefits. And I showed last time that the speed benefit that I got on my RISC-V Sci-5 U74 machine was about 2.5, which was not too far from what I got on my x86 machine with 32-byte vectors. And so exploiting data level parallelism is going to be beneficial regardless of a lot of contraindicating factors.
Okay, so for what you're showing us here, you're specifically showing us how to parse the Zig syntax.
This is specifically for alphanumeric or underscore. So we are producing a bit string where the bit string, there will be a 1 if a particular byte was an alphanumeric or underscore. So it corresponds with each other, right? Each bit corresponds to a byte. And for this specific function, it's going to tell us, is it an alphanumeric or underscore?
But these techniques we could apply to any parser. Any parser
pretty much.
Well, would it still work on Unicode where you have multiple bytes per character?
So the thing is, I mean, we handle Unicode in Zig. We have to do UTF-8 validation. That's not what this specific thing is for. But what this specific thing is for is if I have a variable, if I have an identifier inside of my code, which you can see probably 50 of them right there,
Right.
I'm going to be able to look at the first character and say, okay, just jump past the alphanumeric or underscore characters.
Okay.
And yeah, so instead of looking at each individual byte, I have a bit string that I can query, and in just 3 instructions or so, I can get to the end without any branching, without any having any loops involved.
Well, but what I'm asking about though is you could have a literal string that has the poop emoji in it,
Right.
or if it were JavaScript, you can have the poop emoji as an identifier.
Yeah.
So if I'm not mistaken, sorry, this code is only for a spot where it is expecting an identifier. When it gets to a point where it's looking for a string, it's not going to be using this code. It's going to use something else that's going to be able to more efficiently find the end of the string. So it'll skip past all of the UTF-8 garbage. This is more just for the traditional code where everything is just an alphanumeric identifier or some other kind of operator.
Well, the reason that was not clear to me is because you were showing a line where there's a bunch of things. Well, I guess if it's a Unicode character, it would simply not be in the selection set. So this would still be just as well.
So yeah, I mean, in the context of Zig, it's not like JavaScript where you can have a bunch of crazy UTF-8 characters. But even if you were in such a situation where you were parsing JavaScript specifically, probably what you would want to do is you would want to use this code and say, can I jump to the end of something? And then you can look at the next character and say, okay, is it some crazy UTF-8 thing? Then I have to go into some other code that's going to handle that. But when it comes to just jumping over an identifier that's alphanumeric or underscore, that is one of the things that's the main thing in your source file. The main things in your source file are your identifiers or keywords
Yeah.
or numbers, and then your white space, to some extent comments depending on who you are, and yeah, so we want to get to the end of these tokens as quickly as possible in order to get speed gains. Okay, so this code
Can you
here.
tell us that comments are slower so that people know not to use comments when they can?
I'll tell you this: if you use carriage returns, your compiler will go a little slower, but it won't actually be that bad. But I feel like it deserves to be worse. Yeah.
So you should just write your program in 1 line?
Yes.
Okay.
Yes. Do not use new lines or white space or comments. That.
Sneak a few sleep statements in.
Yeah. Yeah. If you really care about efficiency, that's what you got to do. No, actually, because of these techniques, you can use white space, and it will not hurt you that much because we can just jump over large amounts of white space, and so it would not hurt you as much. Could you scroll up on the left side? And I just want
Which
to.
direction up is? Is this the right direction?
I just want to make sure that we're looking at the right one. So Yeah, we are. So, yeah, if you move that export, if you, like, yeah, select it and then like drag it up to the top, like just the export. Nope, just the export. Just the export.
Oh, we're making a new line. Whoops.
And you
sorry.
like drag it up to the top.
Okay.
You want to export the mask for.
Yeah,
you know,
export the top one.
Oh.
And then you're gonna need a space, obviously. Okay, so you can see the original one was here. This was like 1100 lines. If you could like go to the right and look at that. If you do Control G, -1.
You know, I don't have Control G,
Oh, you don't?
but I have Command G.
All right, well, yeah, this is like 1100 lines. If you go down to my version, if you hit Control Z while selected on the left-hand side a couple times.
I don't have Control Z.
Yep, okay. Yeah, if you go down to my version, you can see, if you scroll down, it's 200 lines. So we went down from approximately 1100 instructions to approximately 200.
You only made it 5 times faster.
So you wrote 5 times as much code and you lost 5 times as much assembly.
Yeah, well, you really got to help the compiler out with these types of things, especially because right now LVM does not have any facilities for automatically producing SWAR code. And there are people working on this, but it's just really in the early days of development. Also, a lot of backends for non-x86 architectures as well are relatively early. I mean, actually, when I started this project, just for the record, I was using Zig's vectors. Zig's vectors directly map to LVM vectors, and it almost could not vectorize anything on ARM when I started the project. Now it's a lot better. It's been worked on a lot. But there are still certain backends where it just completely falls apart. If you try to, like, you can write 3 lines of code and you say, okay, have a vector, do a comparison, do a move mask. And on PowerPC, it's just not in there what a move mask is, I guess. So at the moment, unfortunately, if you want the speed, you're going to have to write it yourself, or you're going to have to get someone to actually go fix it in the compiler, which might have to be me on some of these, because yeah. That was all I had on this slide.
All right, let's move on to the next one then.
Let's move on. All right, so this one's fun. We want to go through this one at a time, really slowly. So this is the interleaved move mask that we can do on ARM. So first I declare a vector called indices, which is, I use that iota thing. The iota function, what it does, it produces a vector that's counting up by ones. And then I multiply that by 4.
I'm a Go developer and all about that.
So, so now we got a vector that's counting up by 4s. Very fancy, I know. Go forward 1. Okay, so there's an interesting thing on ARM that we can do. We can load up, out of a 64-byte chunk, we can load the 0th byte, the 4th byte, the 8th byte, the 12th byte, etc. If we go forward, you can go forward 2 more times. You can see we can load up vectors in this way. There's an instruction called LD4, which is an interleaved load. And so you can load up 4 vectors that looks like this, where the vectors are kind of, they're kind of jumbled. But interestingly enough, this can actually be a lot more efficient for our routine. So
Okay.
let's go forward 1. Okay, so firstly, I'm flipping the order because I don't want to confuse people with, if I say shift left and it goes right. So I'm going to show it a little endian, okay? But yeah, I declare a false vector and a true vector. False vector is all 0s, true vector is all 1s. And then I assume that we do some computation. In this case, we're just checking where the underscore is. And now what I'm showing is each, hold on, go back. Okay, so each individual character represents a single bit of information about the character that it looks like. So, I have, my source file is ABCDEFGHIJ, right? And this is a symbolic representation of the bits of information that we're getting out. And the reason for that is because we're going to do a routine that is going to be difficult to follow if I didn't do this. And so the point is, we have 8 bits of information telling us about A. In this case, it's what is it an underscore? It could also have been, is it alphanumeric underscore? Is it white space? Is it whatever? Okay, so let's go forward by 1. The first thing we do is we're going to merge each set of these vectors, each pair of these vectors. We're going to take just the upper bit of every other vector, every second vector, and the lower bits of the first and the third one. So that's what that looks like. If we want to go back and play it again, yeah.
Okay, so these represent bytes that are loaded into registers, and we're saying that each.
So yeah, each one of these now represents a bit of information corresponding to the letter that you see in the source.
Okay.
Okay. And so at the end, what we want to get is A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, right? That's what we want to get at the end. Because this represents the information, we want to get the information out in the correct order that it was in originally. So we got, like, we did the comparisons to figure out what we wanted to figure out. Is it an underscore? Is it, whatever? And now I'm just saying the information corresponding to that letter is depicted by the letter. So you can follow it.
Okay, so, got it, okay.
Okay. So we can merge the pairs. Okay. Then we're going to merge those two vectors, but we're going to grab 2 bits from the second one, make room, merge it in. And then one more time, we're actually going to merge it in on itself, shifting over by 4. And the reason why we're doing this, you can see now that we have, in each byte, we have a nibble that's unique, or rather, it's not unique. We have duplicated nibbles of all the information we want. All the information we want is in a single vector now. And the reason why we're doing this is because the last 4 things that I showed you, each of these are an instruction on ARM. It's called SRI, shift right and insert. And the next one, the rest of this function is a single instruction as well. It's called shift right and narrow. And what it does is first it thinks about the vector as being 8 U16s. And so we're kind of grouping it together, and we're shifting to the right by 4 if you go forward 1. Okay. Shifting to the right by 4. And then we're turning it back to a byte vector if you go forward. Okay. And then we grab every other byte as the last instruction, or the last part of the instruction. So the reason why we were doing that before, like when we merged it in on itself, was actually because we wanted the nibbles that had information, we wanted those to be next to each other. So we didn't want zeros touching the bits of information that we wanted to get out. And so using this routine, this is actually how we can do an interleaved move mask on ARM. And I can show you the machine code on the next slide, but hopefully that kind of makes sense. Okay.
Does anybody have questions on this? Does anybody understand this well enough to ask a question?
So they don't have a non-interleaved load?
So they do, but the thing is, we can get the information out faster using this. So you saw the code before. What we had to do is we had to move mask each individual vector that was 16 bytes into 16 bits, and then we had to OR them together, shift them and OR them together. With this, we can actually put them together in just a couple of instructions.
So we're doing the same thing so far in the last 10 slides,
Yeah.
or 8 slides. We're doing the same thing. We're just looking at different ways to optimize it for different CPU architectures.
Exactly.
Okay.
I want to ask something. So this thing that we're doing, like x86 does this automatically, right? Is what you're saying, but like for ARM and like.
Yeah. Okay. So when you write the high-level code, it will give you decent vector support on x86. On ARM, it does not give you this today. So.
Right, so what this would actually be is not these characters, but what this would actually be would be a bit stream where each of these would actually be a 1, but because each of them being a 1 would not communicate anything.
It would be a 1 or a 0.
Right, but in this case it would all, I guess this would be a 0, and this would be a 0, because they're not.
Oh, you mean like for the source? Yeah, it's it's not about checking for underscore specifically. It's just getting the bits of information out. After we do the computation, we want to get it out in the right order. That was the point of this. The point was not actually trying to parse that. I don't think you'd see that in a real file anyway.
But what I'm saying is this right here representative of bytes? That doesn't seem to make sense because it's just the same thing right before reversed. Or is it representative of bits, where the bits represent the byte? These are going to
The
be
second
zero,
one.
these are going to be 1 or 0, but you're showing it as the letters so that you can see how the transformation happened,
Yep.
that this one actually corresponds to that A.
Exactly.
Okay.
Exactly. So yeah, at the end we ended up with a bit string that would tell us the information about all those source bytes.
All right.
And it doesn't matter if you're checking underscore or what have you. So this is the unoptimized, or no, this is optimized code. So this is actually showing alphanumeric or underscore. So you can see we kind of need, duplicates of instructions in order to get that done. This is actually on the Cortex A15. This is actually a 32-bit machine, interestingly enough. And this machine, you can see on the ARM instruction set, how it works, the D vectors for 32-bit ARM, the D vectors are 8 bytes, and the Q vectors are 16 bytes. And what's interesting, to me at least, about the Cortex A15 and the A12, they were actually the first processors in their generation to be able to operate on 16 bytes at once. So previous ARM machines, they could operate on 8 bytes at once. They supported 16-byte vectors in the instruction set, but they would emulate it by doing 8 bytes twice, so it would be slower. Okay, could you first move the Cortex A15 down? I have a modern ARM right above it.
Let's see. Can I? Oh, I can. How unexpected.
Yeah, so you can see it's pretty much the same. The differences between them are basically the interleaving that's occurring. But you can see at the bottom, that was the move mask routine I was showing. So the LD4 at the top, and then the 4 SRIs and the shift right and narrow. That is all we need. Could you scroll back up again? I want to show one more thing with the Cortex A15.
So let me see if I can grab this. There's a delay when I'm using this screen, so I can't actually precisely move the mouse.
So there's one more interesting thing. Like I said, we can actually do 16-byte vectors on this particular machine. And this code is actually only doing 8 bytes because in the chunk, I specified that it should be twice the size of a pointer. If you go change that inside the vector to be 16.
Line 3.
Yeah, line 3.
Yes. U16?
Not that one, the other one.
Line 3,
Yeah.
the other.
Yeah.
Oh, the 2?
And the size of, delete that. Yeah, just keep hitting backspace. Keep hitting backspace.
So you want me to hit backspace right now?
Yep, just keep doing it.
Oops.
More.
I hit forward space.
It's okay. It's okay. Just keep. Yep, keep hitting that backspace. Okay, so hit 16. Okay, so now we're actually going to use 16-byte vectors on the Cortex A15. And yeah, kind of a cool thing to me, we can actually do 2 VLD4s. And I didn't even have to use it intrinsic to tell it to do that. I did have to use it intrinsic to get it to generate the VSRI instructions at the bottom. But yeah, what's cool, you can see it's loading into D16 and then underneath it D17 and then D18, D19, D20, D21. So it's actually loading up the halves of the vectors in an interleave fashion. This would be really confusing, I think, for a person to come up with. But that's how it works. If you scroll down on the left, you can see what I had to do in order to get this emit. So that's me using intrinsics. I wrote that.
Which line?
Yeah, on line 50, I wrote an implementation that would work across architectures. And actually, if you were to know inline the function, it will correctly canonicalize it. The compiler will. But when it's inlined, the compiler is not able to canonicalize a lot of things when they get inlined, unfortunately. That is kind of a fundamental limitation, I guess. I mean, I actually don't know the reason why, but a lot of the things in this talk will have to do with miscanonicalization problems. And then, yes, so we have we have the Arch64 intrinsic and the ARM32 intrinsic. If you look at the shift right and narrow, originally I had like a pretty nice cross-platform implementation at the bottom, and it didn't give me the correct instruction on ARM32, and I asked the LLVM person about it, and they're like, oh, it's because you have to double the size of the vector because it doesn't correctly identify half vectors. And I'm like, okay, cool. So that's why it looks weird. But it works, and it works cross-platform, so you can test it on x86, even though it will not be efficient on x86, but you can see if it works.
So let me see if I'm understanding this right. The old way, we'd be doing a loop with lots of branching and several instructions per byte of the
Right.
source code. This one, we have 50 instructions, and we're doing 64 bytes for all 50 instructions with no branching,
Yep.
no loops, and all of the loads happened at the beginning, so basically all the rest of this is going to be blazing fast to
Yeah.
64 bytes.
Pretty much as the CPU can shovel into its execution pipelines, it can do.
So you're probably going to be memory limited then, still, I'm guessing. But
We are typically CPU limited.
still CPU limited, wow.
Yeah. The thing is, when we're doing a tokenization thing, like we're going through contiguous virtual memory, and so our prefetcher is going to work ahead and say, okay, probably we're going to want these chunks coming up, and so it can get it in our L2 cache ready for us. And so actually, you can get serious gains with very small improvements to the assembly. I told AJ I actually made the UTF-8 validator that I use in my parser, but also is used in SIMD UTF, SIMD JSON. This is used by Node and Bun. I eliminated 2 instructions from part of the routine that does UTF-8 validation, and that translated to a 4% performance uplift. Just 2 instructions gone, 4%. And on the one hand, it is a very tight routine as is. It was very well engineered to begin with, and so. But yeah, the thing is, like, once you get to the point where you really are going like as fast as the CPU can really go, memory, we can get memory in terms of bandwidth. It's very fast. We can get a lot of data. The issue is if we did random access and did cache misses to a bunch of random places, then we would be heavily memory bound. But for things like this, we are definitely CPU bound. And anytime we could eliminate 1 instruction, if we could do that 10 times, you can see tremendous differences in the runtime of the application. So.
And if you could do it 20 times.
Yeah, if you could do it 20 times, then
There'd be no instructions left.
there are no instructions
Start
left.
inventing new instructions about it.
Pretty much.
Alright.
So, okay, the only other thing I guess I wanted to point out is with the Cortex A15, it's a 32-bit machine. So you can see at the end we're doing vmove. I believe that's a vector move. So we're moving from D16, that's a vector, into R0 and R1. So that's 2 separate registers. And the reason why is because we're getting 64 bits of information out, but we only have 32 bits in our, that's supported by our general purpose registers. And so we have 2 destinations. And we have to keep that in mind if we actually do want to optimize for these types of machines. And I believe that this situation actually will present itself a lot more going forward. The reason being that right now, if you get the latest x86 machines, finally there is a 1-to-1 ratio between the vector size and the bit size of the word. So that means we have 64 byte vectors on a 64-bit machine. But there are some machines where you can go up to 128 bytes, not necessarily available for consumers at this point, but going into the future, if you are able to get a machine that has vectors that are larger than the size of your machine word, being able to operate on them efficiently is going to require you to store them to a separate buffer and load them out individually. If you were to uncomment that foo at the bottom, that's just a little...
What's the hotkey to uncomment in this?
There isn't one. You have to do Control Shift down, and then okay, you can do that.
I can't believe it.
Yeah. So yeah, if you were to scroll down, so you can see it's 3 instructions. It's 3 instructions on Apple latest. This is because we're operating on 32 bits, because it's a U size. If you change U size to be U64 on line 72, just so we can see,
What?
you're going to have to
That worked
delete
the
some
way that I
stuff.
was expecting. I thought that I had that highlighted.
Yeah.
Highlight.
So if you try to emulate 64-bit code on a 32-bit machine, what you're going to get is
Yikes.
unfortunate things. And that little
Not
piece of
a
code,
trial, baby. I guess it's not.
well, it has to do with it being a 64-bit machine. So
Yeah.
yeah, I mean, if you look at the Apple 32-bit machines, there it would be the same thing.
Nope,
So
not gonna do it.
yeah, so the point of this story is, if you want to pull out 64 bits, you're gonna want to read 32 bits separately once you're going over the data after you already computed it. We can move forward if you want. So it's
I wanted
ARM,
to-
not Arch32. Oh,
Oh, really?
yeah.
Huh.
Yeah, it's a really dumb naming convention in my opinion.
Yeah, well, that happens all over the place.
I don't know if Apple latest is actually going to work. You could do the Apple.
It's silly.
It would give you a list, but there's no point. Okay, so yeah, my tokenizer design, we can reuse the bit strings, as you already said. It can be quite expensive to produce these, and in fact, we can produce maybe multiple of them at once, depending on the machine's width. Width referring to how big the SIMD vectors actually are. Also, this dovetails with the fact that we have to do UTF-8 validation for every chunk. We can actually do that completely in SIMD. This is work not that I did, but that was done by the folks who did SIMD JSON. SIMD UTF is the specific project. So that would be Daniel Meyer, Geoff Langdale, John Kaiser. Those people actually figured this out. Travis Tullock ported a version of it over to Zig, and then I fixed the bugs. And then I also wrote SWAR implementations because for some reason I studied the dark art of SWAR for this project. Yeah, so anyways, I divide up the bit strings into 2 categories. We have bit strings I produce speculatively and bit strings that I produce on demand. So speculative is when we do work before we know that we're actually going to need it. And so we produce 3 bit strings. We want one that tells us where the white space characters. Is it a new line? Is it a tab? I think I'm missing a slash there.
Yes, you are.
Or space.
You're also missing the space there.
Yeah.
That's just
There's
two
kind of
singles.
a space there.
Those are 2 monospace semicolons. I can tell. I know.
Oh, okay. Thank you. And then, yeah, we do the alphanumeric underscore, of course, and then we have control characters. In practice, those should just be a new line, but some people use carriage returns. And we use that for jumping to the end of comments or single line strings.
So when you said carriage returns, you meant actually /R. You meant
/R.
actual carriage return.
Yeah.
Not interchangeably with new lines. So you mean the devil's people. The devil's
Yeah, that's what I'm talking about.
Okay.
Yeah.
Gotcha.
And then on demand, we do the operator continuation characters on demand. So when we see an operator, we're like, okay, how many characters are there after? That is the one part of this project I still think could probably be better. I'm not really sure how. If you look at the code, you'll notice there are like some fundamental reasons why you can't make it that much better, but I tried recently. Unescaped string character literals, of course, that's just too rare to be a meaningful optimization for Zig, where just the number of strings that you have, it's not common enough to actually make sense to find out where the unescaped string and character and like single quote characters are for every single chunk. Instead, you just do it when you see the beginning of one. All right, so this is some idealized tokenizer code. This is what I would have written if my compiler could give me a good emit for this. You should be able to step through it a little bit. And yeah, this one's just chunks. It's not like doing any animation or anything. But yeah, the idea is we produce the bit strings and we write them into a bit strings buffer. So you can see I have 3 slots in it. And then this is the hot loop right here. So let's stay on that one. So I take cur.pointer, that's my cursor into the file, and I truncate it to the log int of uword. So that's going to be 6 bits on a 64-bit machine. I take the lower 6 bits, and that is my position within the 64-byte chunk that I'm in. It's going to be 0 through 63. And then I can pass that into a right shift on the selected bitmap so that I can move the data to the front of the bit string that is the next byte I'm actually looking for. And then I do a count trailing ones, increment cur, and then I check whether I need to go again. Maybe I'll grab the next set of bit strings, but otherwise I'll jump out. I check if it's an end of file. Otherwise, I get the length. I check if it's a keyword. We'll talk about that later, how exactly that works. And then we write out the token. We update prev. So the extents of our token is always from prev to cur. And then I say, okay, depending on what the first character is, I select a particular bitmap from my bit strings buffer, and then I'm just going to loop back around and query those. Unless it is the beginning of a string or a character literal. Then, in this case, I actually just wrote the simple loop down there, but we actually do have something courtesy of John Kaiser that's heavily... Yeah, go back.
I can't get to it.
No, it's okay. That might be the last slide, I guess. But yeah. So the point is, we have a buffer. We put the bit strings in there, and we query them. Whenever we encounter a first character that can be completed by whatever piece of information we're looking for. So, okay. Do we want to move on?
Just real quick, I did have a question.
Go back.
How much of this is, how much of Zig is making this easier to write, and how easy would this be to translate to other programming languages?
So Zig has built-in vector support, and that helps a lot.
All this stuff right here.
Yeah, I will say some of the, what do they call it? The type inference, where it's like, okay, if I have this thing and I'm adding a thing, it infers the type based off of I forget exactly what it's called. But yeah, some of that right now you can see like, okay, I have to say splat it into a vector of this type and then use it, and then make it this type and then use it. It's planned, I think, to help alleviate some of that to make it a little cleaner. But in general, having the vector facilities is a godsend, and I think it makes it a lot easier to write code like this. But again, writing code like this, if you're using LLVM, it's not actually going to give you that good of emit for architectures outside of x86. So.
And Apple latest.
Apple latest, it's okay, but it doesn't do the interleaved routine.
It's okay. It will soon.
Yeah.
I paid $3,000 for it.
Yeah. Okay, so yeah, I just wanted to show real quick. I know some people wanted to see me chase down the last cycle. So this is how we emulate count trailing 0 on a RISC-V machine. I'll just walk through the assembly just really quick. The first instruction says branch if equal to 0. So if it's 0, we're going to jump to that LBB02, and we're going to load up 64 into A0. That's our return register. So if it's 0, we return 64. Otherwise, we're going to start loading that constant into A1 from the LCPI 00, whatever. Yeah, we're going to start loading that. We take the negative of the input, put it in A2, and then we AND it with the original value. So we're saying A ANDed with negative A. So for those who are not familiar with bit manipulation, negative is equivalent to doing a not and then adding 1. And so if you have A ANDed with doing a not and then adding 1, the A AND is going to capture the bits that are the same, the 1 bits that are the same. So the bits that flip twice are going to be the ones that you capture. So if you flip all of the bits and then you add 1, adding 1 is going to flip the trailing 1s to be 0s, and then the lowest 0 bit to a 1. And so you're going to be isolating bits in that fashion. And then you're going to multiply by the constant that you loaded. That constant up top is a special number called a De Bruijn number, and I'll actually show that next. But the point is, you do a multiply, and it's basically a perfect hash function. That's a table right there. You look it up in the table, and you're good to go. Let's go to the next slide.
All right. Does anybody need any of that or want any of that?
Well, the next slide is actually a little easier to understand.
Oh.
So we got if a is equal to 0, it returns 64. Otherwise, a ended with the not of a plus 1. So that's exactly what I said. What that's going to do is it's going to isolate the lowest 1 bit. It's going to isolate the lowest 1 bit because, like I said, if we add 1, that's going to flip the trailing 1s into 0s, and then the lowest 0 bit is going to turn into a 1. Now, if we were doing that on an inverted bit string, we are talking about the lowest 1 bit. And so a ANDed with negative a is going to isolate the lowest 1 bit, which is guaranteed to exist because we just checked if it was 0, and we know that it is not. Now we multiply. Now I load up the De Bruijn number. I showed in binary here because what's interesting about a De Bruijn number is that every 6 bits is a unique bit string. And it's like you go forward by 1. And so any amount that you shift that number, there will be a unique 6 bits in the top. 0 through 63, every single number is possible. And so the lookup table is actually, I wrote out the comp time code where I'm just getting the reverse mapping of how that's going to work. So if I shift it to the left by 5, that's going to give me a specific answer that's not 5, but I want 5 at the end. The reason that I want 5 at the end, if you step through a little bit, I guess it's just going line by line. But the point is, we're going to multiply De Bruijn by x. So we isolated the lowest 1 bit, and we're multiplying by the De Bruijn number. So when we multiply by a number that has a pop count of 1, that is going to be equivalent to shifting that number by the number of trailing zeros, right? We're trying to calculate how many trailing zeros there are, and so we're shifting the bit string according to the number of trailing zeros. We're getting a unique 6 bits at the top based off the number of trailing zeros, and then we can shift to the right by 58 to get those 6 bits, look them up in the lookup table, which is just going to reverse the relationship that I just described.
Okay, so remind me again, the lookup table contains what information did the lookup table contain?
Yeah, so it's the opposite order of the De Bruijn, basically.
No, but it was like identifiers or something, because you're basically creating a hash out of this so that based on the bit sequence you can look up, was it keywords or identifiers?
This is count trailing zeros.
So this is just the count trailing zeros. So it doesn't matter what the information is that we're querying. The fact is we're going to figure out the count trailing zeros.
All right,
and
I don't understand the significance of it. I think you just explained it, but this is all new information for me, so it's all new context, so every slide is like...
This is the fast track of how long is the current identifier.
Yeah.
Okay.
So
once you have the mask, then you do this, and it jumps you to here's the end of that identifier.
Okay.
Yeah, so we take a bit string out, which like he said, is just, it tells us, okay, where are the alphanumeric underscore, where are the white space, depending on which one we want. We shift it over, and that's going to shift in, well, yeah, that's what I'm getting to next. But the point is, we're doing count trailing zeros because we want to know how many more alphanumeric or underscore characters are at this position.
Yes.
That's the point.
Yes. Okay.
So,
thank you. Yes.
And it doesn't matter what the information is. I did link an issue there. I don't even remember what that's for now.
It's probably because they get optimized.
Yeah, it's probably not optimized enough. That's what pretty much all my issues are with LLVM. So, anyways, how do we emulate count trailing ones? Can you edit on Compiler Explorer again because it's doing the weird thing?
Wait, what if I just do this?
That's not going to work.
What if I try?
Just edit on Compiler Explorer.
Fine.
I lose all faith in computers every time. Okay, so this is what it looks like if you do a not count trailing zero. So, so if you look at this assembly, right, it's pretty similar, except now we're loading a -1 into A0, and we're branching on equal. We're not checking at 0, we're branching on equal. So is A0 a -1? If it is, then we're going to jump down and return 64. Otherwise, we start loading a constant, we do a not, we do a negative, we do an and. that is the same x ended with negative x, except we're doing a not beforehand. Okay? Then we multiply and we shift and we do the same as before. Okay? So this is inefficient. If you go to the next slide, you can,
Am I going to close this out?
this is me chasing the 2 cycles on my RISC-V machine. Okay, so here it is written as Zig code. If a is -1, return 64. Otherwise, we're going to make a not a, and we're going to say not a ended with the not of not a plus 1. Does anyone see the optimization here? So
Doing not a twice.
you're taking the not of not a, which is a. So you don't need to do that. You can shorten the instruction dependency chain that way. Also, you might also notice that we don't need to branch on a separate constant -1 that we load up, because we're literally taking the not right there. We could just take the not and say, is it 0? Or actually what LLVM will do, if you go to the next slide, you're gonna have to click a couple times, I think. But don't go too fast. Okay.
Click faster. Don't click faster.
Okay, so what was I going to say? Go back 1 slide. Okay, yeah, let's just continue.
LLVM.
So this is what it looks like on the inside of LLVM. This is the reason why it's giving us bad code here. It's because LLVM, inside of its intermediate representation, has a count trailing 0 as an intrinsic, as an instruction in its idea of a machine. And so when it sees the code XOR with -1, which is the same as a not, and then it sees a count trailing 0, it cannot put the XOR with -1 into the count trailing 0. So the emulation routine for the count trailing 0 will be dropped in without interacting with the not, which is why we see the pessimization there. So there are the 2 optimization opportunities that I pointed out. And I think if you go to the next slide, it will show what we can do.
So, I mean,
So if you click Edit on Compiler Explorer again, because it's doing the thing. So the first one, yeah, can you split screen it for me? Yeah, so the first one is the unoptimized. It's just your basic, I call it with auto. If you call it with always inline, and I wrote my own implementation of CTZ, which is exactly the same as LVM's. But if you inline it yourself, you actually can get this optimization out. So if you look, you can see, for one, this is shorter. But if we add 1, then we branch on equal to 0, like I said. And now this is just a not and an and. And so this is directly computing. Oh yeah, and the add 1 is being fed in with the not. And so we're doing a plus 1 anded with the not of a.
there's a human on the other side of the LLVM, right? And they're making decisions for these things. So is it just like they made this decision 10 years ago when the ARM CPU was different? Or are they just like, let's get this over with and move on, and they're not thinking about it critically?
So I haven't been on the insides of LVM, but what it appears to me to be is an architectural issue. Architecture, I mean code architecture. So LVM is designed in a certain way where the passes are done in a certain order, and it sees the intermediate representation in a certain way. And what I said about the XOR with -1 and the count trailing 0, that is what the middle end of LVM sees. And so the piece of code that can put the not in there and do this optimization, it's not happening unless at the level of Zig, before LVM gets it, I tell it to inline in an implementation so that it can actually see the individual things as opposed to just seeing a count trailing 0 instruction. And by the way, if you put no inline, if you take away the inlining, what you see, the upper function, the reason why it's not optimized is because it actually will canonicalize that count trailing 0 and thereby make it less efficient.
So you're relying on the fact that it can't canonicalize very well in order to convince it to produce an optimization that it normally can't do.
Exactly. I'm relying on a compiler bug and its inability to see what is happening in order to get more efficient code.
All right, so I'm gonna try to rephrase that. So are you saying, like, it's looking at these 2 lines, let's say, and it's looking at these 2 lines, and it optimizes these two lines and optimizes these two lines. But if instead it could figure out these two lines, and then do a pass on the complete output, then it already does know that this intermediate stuff could have been optimized, but because it generated this piece and generated this piece and didn't look at the aggregate of its generation, it couldn't detect the optimization that it otherwise would have known to do.
So I haven't worked on the inside, but I can say, I would do something probably sort of like what you're describing. If I were to write it myself, what I would do is I would say, okay, if I have a function and I can canonicalize that as a single thing, it can be expressed as a single instruction in my intermediate representation, I'm going to hold on to that. Even if I inline it, I still want to know that it could be one instruction. And so if I come up with something worse than that when I inline it, I certainly don't want to do worse. And so definitely if I was writing it, that's how I would design it. That said, I haven't seen the insides of LVM, and based off of the issue that I submitted, it sounded to me like the people describing why it's difficult to fix this is because the way the code architecture is structured. And so part of the reason why I wanted to include this was people who are working on future developments that could eventually replace LLVM. I want to try to have an architecture. Can we before we X out of this? I want to try to have a code architecture that can actually give us good emit. Which by the way, like this is a very very simple example, and it's like from my perspective, it's like I can break the compiler with a not. Like I have count trailing 0 with a not. And I have like two other issues where it's like, okay, I have two nots and the whole thing falls apart. And yeah, so I really want people to think, people who are writing the compilers of tomorrow, we need an architecture that can handle nots, and we need to be able to handle and not, we need to be able to handle these things. I wanted to point out with the one trailing 0 thing, so this one trailing 0, if you scroll down,
This one?
on the left.
Okay.
Yeah. So I wrote, does count trailing 0 equal 1? So sometimes in code there's a situation where you're comparing against a constant, and therefore you don't have to do the full computation in order to do that. So this is one time where it's helpful for the compiler to know this is a count trailing 0. And so if you just put a new line before the declaration of count trailing 0, or sorry, inline, could you do that? Could you put it inline before the declaration of count trailing 0 if you scroll back up?
Right here.
Yeah. Before.
Well, huge step before.
Yeah.
All right.
So if you inline it, you tell Zig will always inline it. Now, if you scroll down, you'll see that optimization is gone. And the reason why is because LVM no longer sees that it's a count trailing 0, and therefore any instructions where it's saying, or any optimization that it might do with the knowledge that it's count trailing 0 is now gone. And so yes, relying on this bug in the compiler to get better performance, you have to know the specifics of the situation in order to know that you're doing it right, unfortunately.
So what about the Zig self-hosted compiler?
Well, the Zig self-hosted compiler right now is not in line for being competitive for optimization's sake. Right now they're just trying to get the test suite to pass so that it will work.
That makes sense.
But yes, going forward into the future, the Zig team is very interested in having competitive optimization passes, and I think there are definitely ways that something could be architected better than LVM.
So we're going to have ZZZ.
Maybe, yeah. So that's all I have to say about this.
All right. Uno mas, uningo
Yeah.
mas.
Yeah. And then yeah, here's one on Spark. I just want to show real quick. If you just type inline before the FN CTZ declaration. So on this Niagara 4 architecture, we have pop count. You can emulate count trailing 0 with a pop count, right? If you isolate the trailing zeros and then pop count them, pop count counts the number of 1 bits. And so yeah, you can see if we inline it, it becomes more efficient on the Niagara 4, and it becomes less efficient on the Zen 4 because now it doesn't see that it's doing a count trailing 1s. It doesn't understand what a count trailing 1s is. And so in my real code that uses all of these, I just say if it's x86, just do that. If it's not, then you can fall back on the pop count or something. And this, basically what I'm doing is the work of the compiler, and I fully acknowledge that. This project is a research project just to see what is the optimal emit and how hard do I have to fight in order to get it out of the various architectures that LVM supports. And I believe the answer is you have to really try hard. I think, I will say in fairness to LVM, I believe they have a disagreement with Zig about whether parameters to a CABI function should have like a poison flag on it or something. And so I think there's an extra, that branch shouldn't be there normally. I think in C it wouldn't be there, and I think the Zig people just have to put that extra parameter, like put the extra thing, the poison flag on the parameter, I think is the issue with that.
What is is that position?
Poison is, it's like, it can be undefined, I think, or not undefined. I don't even know. So there's zero poison and non-zero. I don't know.
Are you saying poison like I drank poison
Yeah.
and died?
Yeah, that's the
Okay.
kind of poison I'm saying.
So it's not an abbreviation. It's
No, yeah, the idea of poison is that it's like affecting the way that the execution happens because you're like biasing it towards, like you're poisoning the well, you know? It's like that. Like you're biasing it before you even get started towards a particular outcome. Anyways. So yeah, I did the cross-platform one. If you just right-click on one of the things and click jump to source, yeah, right-click, right-click, scroll to source. And yeah, so you can just see in my code, I just wrote it out. If we have a pop count, do a pop count. If we have count trailing 0, do count trailing 0. If we don't, then do the emulation routine. It's basically what your compiler should be doing for you. Anyways, I think I've spent more than enough time on this.
So pop count is a what do they call that, a Zig intrinsic or whatever that's called.
Yeah, it's
you still have to check specifically the CPU architecture.
So you don't. If you want it to be one instruction, you do.
Oh, okay, because you have has pop count, but not has like efficient or one instruction pop count.
Yeah,
So
I
then you
mean efficient pop count. That's what I
You
mean.
can't like try compile this and then get the assembly back and then decide based on that.
That's exactly what I did.
Yes.
That's exactly what I did. The other thing you can do is you can just look up like, oh, pop count, is it supported since ARM v6? And so if you look, has CTZ, it's like, okay, I say RBit plus CLZ is close enough. If you have V8A, that instruction extension, then you're going to have it. If you have V6T2 on ARM, you're going to have it. On MIPS, you don't have anything. PowerPC, you have it if you have like Power 10 or something, if you scroll down.
so you okay? Again, I am
So, yeah.
not operating at this level typically, but you are essentially programming. Not essentially, you are actually programming the compiler.
This is the work of a compiler,
You are,
but the compiler doesn't do it.
but Zig gives you easy access to it.
Yeah.
I don't know if other languages. I don't know what
So-
I've never done this in
So,
any language.
like, SymD.json is written in C++, and that is also another project where they are they're doing hand-rolled work that a compiler should be able to
Does
do
it
a
look
lot of
as
it.
easy to read as this, or is it crazy? Like
So how the C++ one works is they define separate classes, and they say if you're on ARM, then the way that you do a move mask is like this, and then if you go look at the x86 file, the way you do a move mask is the move mask instruction. And if you're on PowerPC, then there's like 2 or 3 instructions that can do a move mask. And yeah, the PowerPC one, if you say in Zig, use directly accessing LLVM's vectors, you say bitcast my vector of booleans to a bit string. It can't do that. And I submitted an issue recently, and they're like, "Can you give me the IR dump?" I'm like, "It's 3, it's 3 instructions." I don't know. Like,
What's
it's
an IR
intermediate representation.
Okay.
Yeah. So yeah, it's kind of funny. But anyways, I want to move on. I don't know if anyone appreciated this digression, but yeah.
It depends on how it wraps up.
Okay, so we can use vector shuffles to match white space. This is another optimization. Whoa. Yeah, go one at a time.
I only did one.
Okay. So yeah, a vector shuffle is where we take typically two 16-byte vectors, and the second one holds a bunch of indices into the first one. And in this case, it's just going to look at the lower 4 bits of each element in the second vector. It actually depends on the particular architecture, unfortunately, what the exact behavior is. On x86, how it works is it will just look at the lower 4 bits and do 16 simultaneous table lookups based off the lower 4 bits, or if the uppermost bit of a byte element is set, it will 0 it. On ARM, if you have an index that's out of range, it will 0 it. On PowerPC, it will just look at the lower 4 bits, it won't 0 anything. MIPS, it's the 6th or 7th bit. WASM, it's if you go out of range, it will 0 it, I think. And yeah, so different architectures have different ideas about how this should work. But the basic idea works. This is definitely something the compiler should be able to do, which is when I have a vector and I say, okay, where are the spaces, tabs, and new lines? And let's go forward one.
All right, so first of all, what
It's going to show the same thing again. Just
what
go
does
forward.
this represent? Because I don't know what this
Yeah.
means yet.
So this is hex. This is the characters as they normally appear. So the idea is that each of these characters is going to look up inside of this buffer simultaneously, 16 bytes. So the lower 4 bits of each of these is going to index into the top one. So you saw that shuffle occurring. That was each individual one of these pulling the byte from the top. And so the idea with this is we can make it so that a new line is going to grab a new line, and a tab, I don't have a tab down here, would grab a tab, and a space corresponds to a space because the lower 4 bits are the same. And then what we do is we compare these two. We compare equal. And we say anytime they're equal, then we know that we matched in this particular set. So in this case, new line is going to pull a new line over to it. We say, is a new line matching a new line? Yes. And for tabs, if this was a tab, this is a 9 like character, so that's 39 in hex. So the lower 4 bits are the same, but this is not a tab, and so when we compare it, it's going to say it's not a tab.
Okay. Wait, so are you saying? Okay, let me back up one.
Yeah.
All right, so we look at this.
Yep.
The top row represents the table where
Yep.
the lower 4 bits are the address.
Yeah.
Okay, and the bottom row represents the actual text.
Yeah.
Okay,
So-
and the middle row is
Table indices. So these are indices into this table.
but they're
Just the lower 4 bits.
They're characters, but the lower 4 bits of them are used to index into that table.
Yes. So we look.
Because if we have a match in the lower 4 bits, then it is highly likely.
So it's not about likelihood. It's about the fact that we are grabbing the bytes that we're targeting. So a new line is going to pull that new line over. So a new line is 10 in hex. So the lower 4 bits will say 10. And so we look up 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What do you know? There's a new line there. And so it's going to move the new line over because there's a 10 here. So we're indexing into it. It would be like if we go over each byte and we look at the lower 4 bits and we look it up in the 16
And
byte
so
table.
Y is the case where the lower 4 bytes of Y are the same as the lower 4 bytes of, bits of tab.
They're both 9. They're both 9. So I actually have it here. It's 79
Okay.
in hex.
Oh, okay. This makes more sense now when you're
Yeah.
showing it in hex because the lower 4 bits are the
Yeah.
rightmost digit.
Yeah, so
Got it.
these two things are the same.
Okay, got it.
One of them's hex, one of them is the characters as you would see them visually.
Okay, got it.
And so yeah, when there's a 20, we're going to grab that 20, but actually when there's any 0 in the lower nibble, we're going to grab that space.
Right.
So that's why we need to check, and we need to say, okay, is it equal? And so it's not about likelihood. We can tell with a certainty whether something is a space, new line, or tab. We can classify all 3 of those simultaneously using a vector shuffle.
Okay, and so what this is saying is that we can take up to, for example, on x64, up to 64 bytes at a time, and in a single operation, well, 2 operations, we can find all of, with the shuffle and the and, we can find all of the matching bytes.
With a shuffle and a compare equal.
Compared
We-
to,
I'm confused about
Yeah.
something. So like the slash and n example, right, it grabs like the ninth,
So slash n is 10. Tab is 9.
sorry,
Yeah.
is the fact that the top one, or the 10th index on the top table, the slash n, is that a coincidence or is that constructed specifically for this? Or?
No, it's constructed specifically for this. So what we're trying to do is we're trying to tell, is it a white space, like is it a space, is it a tab, or is it a new line? That's what we're trying to tell. So this,
Right. So the top table then, is in practice, would that be like characters?
yeah, so I'm sorry, the top table and the first set and the top table and the second set, they're the same. So the first one is representing as hexadecimal. So you can see each nibble represented as a base 16. And the bottom one is just like how it would be printed. It's a printable character.
Right.
But it's the same thing. So we have 20. That's the character for space. I did put underscore so you can like see something there. And the dots I just used to represent zeros. So you're going to get zeros moving there. And yeah.
and this really just works because you happen to get lucky in a sense. Like the white space characters happen to be close enough to each other and happen to not conflict.
Yeah.
That we're able to do this, but
So the way that they could conflict would be, I mean, if
like
the
if
nibbles
ASCII
were,
defined slash in as another 16 characters away from
Yeah.
slash t,
if it was 79
Or
or something, then yeah, we would need a different trick. Yeah.
right?
Yeah.
Okay, so it's just a trick that happens to work because we happen to be looking at a character set. But I guess that in encodings, in the way that computers have been designed over the years, this is something that happens frequently enough. What was the use case of this? I imagine it wasn't to compare ASCII.
Matching white space. This is matching white space.
No, I mean the vector shuffle. What's the
Oh.
what's the
So
general
vec-
case of a vector shuffle? Because I can't imagine that.
You can do a lot of things, and I'll be mentioning more things.
Okay.
Let me say real quickly. So the SIMD UTF, pretty much like that is a lot of vector shuffles. And I just want to explain really quickly. So there's different terminology for what constitutes a shuffle versus a permutation versus a swizzle, depending on the specific architecture.
Swizzle? Are we talking about types of children's popsicle, or
Maybe, yeah.
because I'm pretty sure I had one of those in the 90s.
So a shuffle in x86 land specifically refers to 16 bytes. Now you can actually do 4 of these at once inside of a 64-byte vector, but it's going to be 16 bytes doing a shuffle, 16 bytes doing a shuffle, 16 bytes doing a shuffle. It can be all at once, all in parallel, but it's not anywhere to anywhere. It's only shuffling within those lanes.
Would it be the same 16-byte strings, or could they be different?
They can be
16 bytes?
different
Or the same.
or the same.
Okay.
And we like to use it the same typically, because that way you can look it up in the same 16-byte table across 64 bytes. And 64 bytes in parallel, you can look at the lower 4 bits and index it into a 16-byte table if you just duplicate the table 4 times. I personally can't imagine a scenario where you would want them to be different for that specific thing. But yeah, there are a lot of use cases for vector shuffles, and this is just one of them. SIMD JSON makes use of it for character classification in general. SIMD UTF uses it. Actually, what they'll do is they'll take the upper nibble, they'll shift it over to the right by 4, and then they'll take the lower nibble, and they will look both of them up in a table, and they'll AND them together. And I actually do have a screenshot of that if our images work. I don't remember if we downloaded those. But the point is, we can like figure out what set something is in using that. Wajek Mula also has a way where like you could look up a specific bit inside of a 16-byte vector, and you could look it up that way. So there's a number of different things, a number of different like classes of queries you can do. You can put things on like separate channels where you have 8 bits, and you'd say, okay, if I get the 3rd bit and the 3rd bit, and I put them together, and it's a 3rd bit, then I know that it's a space or something. Or I know that it's a 2-3 continuation character for UTF-8 decoding. But yeah, there's a lot of use cases. This is just one basic one that unfortunately the compiler does not do right now. I actually got this idea from this YouTube video, the Easy Perf guys.
So is this like significant less instructions than doing alphanumeric masking?
Yeah, so if we could edit on Compiler Explorer again.
Oh, okay. And how many more slides do we have approximately?
Probably.
Because we are an hour and a half in. It is almost 9:30.
So this is before, if you switch the export to be the export with the mask white space with shuffle, you can see,
Oh, okay.
yeah. So switch the export so that it goes on the next one.
So about how long
Yep.
do we have here? With the slides.
We can cut it soon. We'll cut it soon. Okay, so yeah, if you scroll down past the table, you can see
Scroll down where?
just down on those sides, yeah.
On these?
Yep.
Oh, okay.
So yeah, you broadcast the table, you shuffle, compare equal. Same thing on ARM, you can do that. I even made it so it would work on the 32-bit machine, but we should probably move forward. But you would actually have to do 2 table instructions because it only has it can only do 8 bytes at a time. But on ARM, you can do multiple lookup tables. You can put them together. So you can do, there's table 2, which will do 2 8 bytes to get you a 16-byte lookup table. There's also table 3 and table 4. So you can actually look up 32 bytes on your 32-bit machine. On a 64-bit machine, you actually have 64-byte lookups in parallel. 16 bytes looking up at a 64-byte table. So kind of cool. Let's continue. Okay, keyword lookups. This is how we do keyword lookups. Okay, so I assume that it's export, the len is 6. We go do our hash function. This is a minimal perfect hash. Can you go forward? And yeah, we just do some math here. We grab the first 2 bytes, the last 2 bytes. We do a shift, an XOR, multiply, and a shift.
Okay, and that's where, based on the bit sequence you get back, you're looking up in the perfect hash function to get the identifier without reading the bytes. Is that?
We're getting there.
Okay.
So yeah, so you pass that raw hash into a map to index function. So let's go down. And the map to index function, what it's going to do is it's going to use Phil Bagwell's pop count trick. So the idea, you can see, if you go forward by 1, you can see we have these 2 masks here. So you could, my hash function was mapping to 7 bits. A 7-bit address space has 128 slots in it, and I can represent that with a bit string. And the idea is instead of having a table that has potentially 128 slots, I can compress that to be exactly how much I need, with the exception of 1 element at the end, using this bit string technique. So I think if we go forward, we might have an animation. Yeah. So first thing we do, we take 96, we end it with 63. So we're taking the piece of it that's supposed to go into the second lookup table, and we do the shift by that 32, which is just what we happen to get out. We subtract 1. And then what we do is we're going to take the and of this, if you go forward by 1, and then we pop count it. So the pop count is 17. And so because we're looking up in the second mask, that's relative to the first one. So we do 17, go forward 1. 17 plus 21, which is what's in the first mask. And that will get us 38 out. And so what we just did is we mapped a hash that was in a 7-bit address space, so 128 possible values. We just mapped it into a compressed table which only has 50 slots. And so yeah, if you go forward by 1, oh, did we miss it? Go back 2. 1 more. Huh, okay. Well, we get a hash of 38. Oh yeah, it's because we're not doing it yet. Okay, so yeah, we can look it up inside of our compressed table now. We get export, and then we can read in the keyword. And we are reading in 16 bytes, so we need to over-align our file in order to be able to do that safely so we don't run off the end of a page or something. And I put dots there just to show it's some bytes that are something. It could be anything. Undefined. But it is defined that it should be safe so long as we over-allocate. And I actually put a compile time check to make sure that that happens.
You put 6 there because that's the length?
So 6 happens to be the length, yes. So how it's working, this scheme, what it's doing is it's putting the lengths repeatedly after each keyword. So if you were to go look at that table at the bottom, you will see the lengths duplicated over and over. And then using that select operation that Zig provides, we can say, okay, if we go back to, we can say, okay, wherever the length is greater than counting up, that's when we're going to take the length vector. Otherwise, we're going to take that. So we're just putting the lengths in the right spots. That way, we can compare the keyword and the lengths in one go. So single branch. It's not a single instruction. It's like 2 instructions. But yeah. So this is what a lot of people have wanted to do with very efficient code. So yeah, this is the emit. And so yeah, you can see where this is us going through the hash function. So yeah, I mean, I see a BZ high and a pop count. That's the 1 shifted to the left, -1, do a pop count, and then we conditionally add the first mask into it. But the point of the story is that, yeah, so we're doing a max, and then we're doing a blend, and then we're XORing, and we're testing to make sure we got all zeros out. And so yeah, with a single test, yeah, we eliminated branching, and we were able to check if it's a keyword without branching. I mean, we need to branch, say, if we need to check for a keyword, but within the loop itself, there's nothing going on here. We can just check 16 bytes versus 16 bytes. This happens to work because Zig does not have any keywords longer than 16 bytes. If we did, then we'd have to go up to 32. But yeah.
So language optimization, don't make keywords longer than 16 bytes?
Exactly.
Hashtag legit.
Hashtag legit.
You could still do this and then just have some check that if you hit the first 16 bytes of that.
Yeah, but it's slow down your parser by like 50%.
Yeah.
Yeah. So this is the SWAR emit for my Sci5. If you right click and click go to source on some, yeah, right click, scroll to source. Hopefully it split screens it. It didn't. Okay. Well, if you could scroll up. You could scroll up.
Already installed.
Okay, so yeah, that's the basic lookup that I was showing you. By default, LVM doesn't do a good job. Let's move the export down to the one that I wrote by hand. That was very painful to write.
Oh, it's so painful to use this screen. Oh.
And yeah, basically the idea is when you do a load that's not guaranteed to be aligned by the type system, LVM currently will emit 8 byte loads, individual byte loads. And then it will shift them and OR them together. So to do a single 8-byte load, it is extremely computationally expensive, and we have to do 2 of those. And so LVM does not give us very good emit. However, if we make guarantees about the pointer, this is something I want to have added to the Zig type system so that we can guarantee that it's safe and so that the compiler can do this transformation automatically, which is go back, do an 8-byte aligned load, go forward, do an 8-byte aligned load, again, so long as we can guarantee that that's safe by when we actually allocated the memory. And then we can do a shift and OR them together. And so we're only doing that with 2 loads rather than, 16. And so we dramatically reduce the amount of work that we have to do. I actually haven't looked at this code in a long time, but...
So if you were to store it as a U32 instead of a U8, would that be enough? Like you have a keyword as a pointer to the, like a U8 pointer?
So the problem is in the source file, we don't know if...
Right, because it won't be aligned in the source.
Yeah, we don't know if it's aligned in the source file. And in fact, it probably will not be. And so we have to go back, do an align load, go forward, do an align load. But in the buffer, we can guarantee that it's aligned because we can just say, oh yeah, it's a buffer that's aligned. I just pad everything, so it's going to be, everything is 16 bytes. in memory, and so I can very efficiently pull that out if I'm on a machine that doesn't support unaligned loads. So yeah. That was another thing too, by the way, why my idea for the specific way in which I reuse the bit strings for the tokenizer. We're operating like with 100% aligned loads because we're going chunk by chunk by chunk, and that means that that means that machines that do not support efficient unaligned loads or unaligned loads at all can do it. Okay, this was just another optimization.
So-
I noticed the following code in Zig's AST gen.
I wanna bring this to a close.
Yeah, this is like one of the last
Okay.
ones. But yeah, this is one more optimization. We had this function in AST gen, or we still have it, where it will go byte by byte looking for the new lines to figure out what line we're on. And I figure, I'm like, well, I'm already producing these bit strings that tell me where the new lines are. And so I can actually produce these passively. And the way that I do that is by staggering them in the buffer. So instead of having three slots in my buffer, what I actually do is I allocate enough space to fit as many as I need for the size of the file, and I will just move forward by one each time, as you can see. And at the end, if I were to do a write of ABC shifted over by one, ABC shifted over by one, ABC, at the end I'm going to get all A's, minus a BC at the end. And so I can passively produce this without actually consuming another register, without consuming much extra computation at all. It's going to be like an additional add instruction is what I need in the loop that produces the bit strings. And
All right,
so,
sorry, in this case, I don't know what ABC represents.
So ABC represent the three different bit strings that we produce. So we produce the alphanumeric underscore, we produce white space, and we produce control characters. And the control characters should only have new line, and I can pretty easily guarantee that by having a contract and saying, okay, if there's a carriage return, I'm going to go XOR it out so that we actually get just a new line bit string at the end. And so yeah, so the A's would represent the bit strings that tell you where the new lines are. And so that means that later down the road, we can consume that here. Rather than going byte by byte, we already have that information without much overhead added to the part where we produce the bit strings. So that's the point of that sideways diagram. It's just a staggered staircase looking thing.
Okay, so what? Help me understand. I'm still.
Yeah.
I'm halfway there.
Okay.
The-
So-
the reason you're showing it as a staircase is because
Those are like the writes that we're doing.
your rights where.
So what we do, so we want to have a buffer that holds a bunch of words, 64-bit integers, that tell us where the new lines are. That's what we want at the end of the day. And my tokenizer is already producing the information required for that. We already produced a 64-bit bit string telling us where the control characters are, where the alphanumeric underscore characters are, and where the other space characters are.
Yes.
And so typically we write that into a buffer that has a size of 3, and then we just select,
Size of 3 bytes.
a size of 3 U64s
Okay.
is typically what we would write it in without this idea.
Okay.
But with this idea, what we can do instead is we can allocate enough space, basically 1 bit for every byte up front, and instead of storing in a 3 U64 slot buffer, instead of putting our bit strings in there, we're going to put our bit strings in a pointer that's moving. And every time we grab a new chunk, we move it forward by 1. And then, writing those bit strings in there, it allows us to access it as we're doing tokenization. We can access the A and the B and the C at any given point. But at the end of the day, if we're moving forward by the size of a U64 every time, we're going to end up with a buffer that's just filled with A's at the end. And A represents new line bit strings. And so we can use this idea to passively produce new line bit strings that can be consumed later in the pipeline without having to redo that work, without having to go byte by byte.
Oh, okie dokie. All right.
So
I think I understand.
it's important that A is first because we care about like using the new lines later more than we care about using like B and C or whatever. those-
Exactly. So the B's and the C's are getting overwritten by A's.
Got it, okay.
So the new lines can tell us things like the line number.
The line number. That's what we would use it for. And it would be more efficient than looking at bytes.
Okay.
We could look at bits instead. Factor of 8, more efficient in terms of memory usage.
All right. Well, despite my saying we need to wrap this up and then taking forever to get this, I want to understand this stuff.
Mm-hmm.
Like, I don't know how I will personally use it, but I want to understand it and as much as, yeah, anyway. But, yeah, so we're wrapping up.
Yeah, so this is just a link to Daniel Meyer's stuff, SIMD-JSON, SIMD-UTF, and
What in the world?
well, all right, let's not do that. The end.
The end! All right.
Yeah.
You didn't
So-
finish the last of the presentation?
Yeah, so the other stuff after it would be for the second pass of the compiler, which we could go into at a future date.
All right.
But yeah, the point is, with this project, I've been able to identify problems in existing compiler technology, see where there's room for improvement, and also think about designs that we can actually take advantage of in the future to get more efficiency out of our machines. Likely, the way that CPUs will improve is we can get more width. We'll be able to do more bytes at once in the future. And yeah, if you want to get the same speed ups that you've been used to historically, starting to think in this way where you think about, how much data can I consume at once? Can I eliminate these branches? What can I do to make it easy for the computer to actually do the work that I'm trying to accomplish? Some of these techniques can help.
Well, number one, we can get rid of the x64 processors, and that's happening soon.
x64 is not that bad. It's like
It's power hungry. But
it's
but the good
it's
news
power
is
hungry.
It's going away soon.
It's power hungry, but it's also designed to be power hungry because that's the trade-off being made. Like ARM is definitely more power efficient, but there are power efficient x86 chips too. Just no one buys them because why would you?
Exactly.
I mean,
And it's good. It's going away soon.
yeah.
Yeah, I just, like, I'm looking at this and I'm seeing what you're saying, but then at the same time, I'm thinking,
Yeah.
if we could only get React developers to
So-
use input rather than 5 dependencies to emulate an email field, we'd get like 100 or 1,000,000 times gain. And then we can make it 10 times faster on top of that.
Yeah. So So the results, how fast it was on my machine, it's about 2.75 to 3 times faster than the mainline implementation, which is just based off a deterministic finding state machine. And even on my RISC-V machine, which does not have vectors at all, it's about 2.5 times faster. On ARM, I have only had someone test it without the better move mass routine. And so, yeah, maybe you could test that. But yeah, at that point, it was like 2.2 times faster, but with better instructions, I think it should be closer to 2.5 is what I'm expecting. And like I said, if you can actually make that hot part of the loop faster, if you can actually deal with more data at once, you can expect a lot more gains. And so this is a design that I think, going into the future, as width increases, we're going to be able to get more gains, more speed.
Why would width increase?
Well, I mean, why do we want it to, or why is it physically possible for it to?
I mean, I imagine it's physically possible to because we can put more traces on a circuit board somehow still, even though it seems like we're approaching the limit of that. But we stopped, we had good reasons for going from 8 to 16 to 32 to 64, and then in GPUs, we have good reasons for going to, I don't know whether up to 2,048,000 or something, but a general purpose processor, You know, because at first when I was there for the 16 to 32 kind of sort of. I mean, I was born, and I was definitely there for the 32 to 64. And back in my naive days, I thought, oh, and the 128 is going to be next. The computer's going to be so much faster because I did not understand what bit width meant. But it seems like we don't. I don't know what the like we needed to go to 64 bits so that we could have like exabyte file systems and more than 2 gigs of RAM and but why would we need to go to 128?
Well, could we just increase the vector sizes? Would that be the reason?
Yeah, so that was part of what I was addressing with that ARM machine, which is where the amount of data we can produce through the vectors is actually bigger than the word size. And I'm saying that I think that that's probably what we're going to see. We're not going to see machines that have very efficient 128-bit operations. I think fundamentally you have to, you can't do it in the same amount of speed that you could do a 32-bit addition if you want to run at 5 gigahertz. But yeah, to the point, it's like we can increase the width of the vectors, and we can just produce more of those bit strings at once, and we can go back and grab that data. And so every like fourth time we go into the loop where we might produce the bit strings, we would actually do the work rather than every single time. So.
All right. Well, I'll go ahead and end the stream. We've preserved this for future generations. Hopefully, the knowledge doesn't die with you.